All right, engineering physics students, the second part of this unit is going back to revisit chapter 3, thermal physics, okay, and seeing how we can apply our knowledge of gas laws to actually do something interesting with it, which is to calculate the relationship between heat and work done by an expanding gas, okay? This is really important when you're designing engines, so at the end of this unit, you'll be able to start to analyze the efficient work done by an engine and how an engine process actually works. All right, so the big idea here is to go back and review a few of the concepts that we've done in chapter 3, which is especially understanding how we can model the energy of a gas. Okay, now why are we looking at a gas? Well, a gas is a lot easier to model the energy of. Remember, chapter 3 was all about modeling. And the only thing that we can actually model in nature perfectly in terms of the thermal properties is a gas. And that's because in a gas, the energy is only related to kinetic energy. Okay, in an ideal gas, you assume that the gas particles don't have any interactions whatsoever. The collisions are elastic, so any heat energy that goes into it goes into kinetic energy, which really simplifies the way we do things, all right? And I remember in the end of chapter 3, there was a little bit of a complicated equation derivation, mainly, as Adam pointed out, due to a misprint in the textbook, but you can fix that pretty easily, where you were, in chapter 3, a big part of it, you were supposed to come up with a formula to calculate the internal energy of a gas related to the temperature and the number of molecules of a gas, okay? So what I want you to do before we go on any further is just try to go back. Imagine you're doing your IB exam. Go back to that last part of internal energy in chapter 3 and just revise the derivation for the equation. We're going to use that equation a lot, okay, right? So let's go take a look here. So here I got a piston, okay, like we did in chapter 3. And if I put a Bunsen burner under the piston, what's going to happen? Well, first thing that's going to happen is heat energy is going to go into the piston, okay, and that's going to raise the kinetic energy of the particles. Why? Because the average temperature of the particles are going to go up, which is a measure of the average kinetic energy. And if these particles are going faster, they're going to have a greater change in velocity when they collide with that piston. And remember, force is related to the change in momentum. Okay, that's Newton's second law. So there'll be more force on that area, causing an increase in pressure on that piston. And when the pressure inside of that piston increases, we know that the volume is going to increase due to the ideal gas law. Okay, so we know this relationship. But what we're going to look at in this unit is to try to figure out how much work and how much change in temperature would happen inside of that gas as a result of that expansion. Okay, we want to convert that heat energy, how many joules of heat energy, into useful work. Okay, that's what we want to do. Imagine this is your car, you're burning gasoline. Okay, and then that heat from the gasoline comes out inside the piston. We want all of that heat to do work. We don't want that heat to just be heating up the gases. We want it to be doing work. So we want to trick the system into doing all that heat energy into useful work. And that's something that we'll be able to answer later on. Okay, so the questions that we're looking at right now is how does heat affect internal energy of a gas in a system? And what happens to a system when the internal energy of the gas is raised? Okay, that's the main goal for this first part lesson. Okay, so first of all, let's go back and think about internal energy in terms of the Boltzmann distribution. This was in chapter 3. So a Boltzmann distribution gives you the distribution of all the kinetic energies, or actually the particle speeds, okay, of a particle, which relates to the kinetic energy in a material as a function of temperature. And if you remember, as you heat up, you're going to make that distribution wider, okay, so the frequency of particles goes down. If you look at here, that would be the average kinetic energy of the particles, okay, and that average kinetic energy gives me my average temperature, okay, but this is particle speed, so that's my average speed, and then I can easily plug that into an equation to find the average kinetic energy. That's where these temperatures come from. As you raise the temperature, you broaden the curves, okay, and underneath that curve would be the total number of molecules that have that distribution of energy. So if you want to go back to understand Boltzmann distributions, it's a good idea in chapter 3, okay, because you're going to have to go back and understand the Boltzmann constant, okay, and where does it come from. Okay, so this formula over here is the average kinetic energy is equal to 1/2 m times the average speed of all the particles in a distribution squared, which according to Boltzmann is equal to 3/2 times kBt, okay. All right, so kb is the Boltzmann distribution constant, and T would be the temperature. Okay, so the average kinetic energy is directly proportional to the temperature. That's where this comes from. All right, so the internal energy of an ideal gas relates to the total particles in a system. Okay, so this is the average, but if I want to calculate the total energy, I have to take that average and distribute it amongst the total particles. So the total number of particles, n, times the average kinetic energy is going to give me my total energy, right? And then what we can do with that total energy is what we're after in this unit, okay? So just another thing I want to remind you of, the total energy is going to be equal to 3/2 times n kBt. Remember, 3/2 kBt is my average, so then 3/2 n kBt is my total energy. And we've derived that before in chapter 3. Kb is the ratio of the universal gas constant divided by Avogadro's number. So if I plug that into that formula, okay, my internal energy is equal to 3/2 times n, the total number of particles, times r over Na, times T. N divided by Na, number of particles divided by Avogadro's number, gives me moles. Okay, so another version of internal energy is 3/2 times the moles of particles that I have times the gas constant times T is going to give me the total internal energy. Okay, so remember we had this relationship, PV is equal to nRT. That's interesting. So I guess and we've done this before, internal energy can also be 3/2 times PV. All right, that's kind of cool. And therefore, if I had a change in internal energy, the change in internal energy is related to the change in temperature. Okay, if I change the temperature of a gas in a cylinder, it's going to change the internal energy. And likewise, that change in temperature of a gas in a cylinder is going to cause a change in the volume. Okay, and that's a super important relationship. Okay, so if I go back up to this picture, you can see that as we change the temperature of the gas, we cause a change in volume related to not our general explanation of PV equals nRT, it's related to internal energy. I can derive that change in volume as a function of that internal energy formula, which is very important if you're looking at engines, okay? And that's the goal of what we're doing for this unit. Not looking at just PV equals nRT, but being able to understand the changes in volume and work done as a function of changing the internal energy, and understanding that that change in internal energy is related to the change in temperature, okay? So the second part of this unit focuses on understanding thermodynamic processes, okay? So what we know from thermodynamics is that energy can't be created or destroyed, only transferred from one means to another. Hot always goes to cold, okay? Those are the laws that we learned in chapter 3. But we're going to be looking at some other thermodynamic processes with reference to a functioning system, okay? System. So a system is enclosed, okay? The system that we're looking at here is an enclosed or it doesn't have to be closed, we'll talk about that in a second, but a system is a collection of materials in one space, okay? And then when heat is transferred into the system, we're looking at that system, okay? And then the system can either contain that heat or it can move that heat to the surroundings. That's all outside of the system. So system versus surroundings is a very important distinction when you're looking at thermodynamic processes, okay? And whether the system is open or closed, like I said, this system here, let's imagine, is closed because there's no way that heat can be trapped, can be released. Okay, imagine these are very insulated containers. But if it was open, all that gas is able to escape, or the heat is able to escape. Okay, those are very different types of systems. The next thing that we're going to be talking a lot about is work. Okay, how to calculate the work done by the system, the change in volume, and then understanding what really is the first law of thermodynamics, okay, which is down here, and then being able to interpret PV curves. We're just going to do one in this video, and then the next video we're going to interpret a lot more PV curves. Okay, so according to the first law of thermodynamics, okay, that's the conservation of energy, but this is a different relationship where we're looking at the conservation of energy, but in relationship to heat and work done by a system. Okay, so it's very different than the one you've learned in chemistry and the one we covered before in general, but it still is conservation of energy, all right, in that fact that that heat that I would be putting into my system, Q is the heat added to my system, that Q can be distributed into different things. It can go into changing the internal energy, or it can be actually gone into doing some work, okay? So we're looking at where does that heat get distributed, all right? So delta U is the change in my internal energy, which is equal to the heat I added to the system minus the work done by the system, okay? So if the heat that I put in here, let's say 1,000 joules, goes in and the work done by the system is 500 joules, then I would have 500 joules going into the internal energy, which would relate to the change in temperature. That's one way of looking at that. So how does a system perform work? Okay, well, we've done this before also in chapter 3. Work is equal to pressure times change in volume. And if you just do the unit analysis, pressure is force divided by area, newtons per meter squared, times volume, which is meters cubed. If you do that and cancel units out, you'll get Newton meters, which is force times distance. Therefore, work is equal to pressure times the change in my volume of a system. So if the pressure in here stayed the same, and then I had a change in volume, that pressure times the change in volume would give me the work that was done by that heat going into the system. Okay, so let's take a look at a sample problem. Okay, an amount of heat equal to 2,500 joules is added to a system, and 1,800 joules of work is done on the system. What is the change in internal energy of the system? Okay, so the formula is delta U is equal to Q, or delta Q minus delta W. Okay, and what does this look like? All right, so let's just draw a piston. I got a piston. Sorry for the poor drawing. And I got a bunch of gas inside. This is the before state. Okay, and then obviously heat is being added, so I got fire. Okay, that's my fire. So the heat is being added into the system. Okay, but as well, work is being done on the system. So what does that mean? If work is being done on the system, if work is being done on the system, work is going that way. So my piston has to be going down. Okay, so then after work was done on the system, it compressed it and heat was going in. This actually happens in a diesel engine, for example. Okay, so heat is still going in as the gas is being compressed. And what's going to end up happening is that gas is going to become superheated, and we're going to try to figure that out right now. Okay, so the change in internal energy of my system is going to be equal to 2,500 joules. Now remember, delta W, the work done by the system. So if the work is being done on the system, it's going to be negative. Okay, right? Because work is being done on the system. So if I erase that, it's going to be negative 1,800 joules. Okay, so then my delta U, my change in internal energy, is going to be around 4,300 joules. Okay, and remember that the change in internal energy is equal to 3/2 nR change in T. Okay, so my temperature is going to be changed by 4,300 joules. Okay, that's pretty cool. So that's an example of how we can superheat a gas. You're heating it and you're doing work on it at the same time by compressing it, and that gas is going to get super, super hot. Okay, so last thing I just wanted to introduce is the PV diagrams, which is a very important part of the second part of the unit. Okay, so if we graph inside of these pistons, so if I take a look at this piston up here, and if I have a pressure sensor, and if I have a volume sensor, and I have a temperature sensor in there, I'll be able to make a graph of basically gas laws, PV equals nRT, okay? So if I take a look at this simple graph that I have down here, this PV diagram, what's happening is the pressure in the system is changing, it's decreasing as the volume is increasing, all right? And if I had a temperature sensor in there, in this graph, the temperature always stays constant, but the pressure is decreasing and the volume is increasing. So N, R, and T are staying constant in the system, just pressure and volume are changing. So when I added heat into the piston, okay, I saw this effect. Okay, so all this is happening when we're adding heat into the system. So as we're adding heat into the system, I saw this effect. The pressure goes down, the volume goes up. Okay, then the area under that graph is going to be the work done, right? Because pressure times volume is the total work done by the system on the surroundings. All right, so pressure times volume, that area under that graph is going to be the total work done by the system. Now this, if the temperature doesn't change as the pressure and volume are changing, that's called an isotherm. Okay, that's like a typical PV graph. Okay, so PV equals nRT, pressure and volume, according to this relationship, are inversely proportional. All right, so that's your typical pressure volume graph when N, R, and T are constant. We've done that in chapter 3, and that's called an isotherm. If I change the temperature, the whole isotherm is going to change its position, okay? All right, but if that temperature is constant, that's what an isotherm looks like, okay? And the area from point A to point B, the area is going to be the work done, okay? So what does that look like, okay? If I put a fire under the piston, okay, that piston has to have very, very, very low friction, okay? It's really easy to move, okay? So that as the heat goes in, the molecules immediately gain kinetic energy, and that kinetic energy, when that first molecule heats up and it bounces off the piston, it's able to transfer its force directly to the piston and cause it to move. So there's no lag time, okay? So as the heat is going in, the temperature of the gas isn't changing. All of that heat is going into doing work, okay? The force on that piston. Okay, so the temperature of that gas always stays constant, okay? It'd be hard to find a process in real life that follows a true isotherm because there probably is friction and there'd be a bit of a lag time. But in the perfect world, if something is an isothermal process, when the heat goes in, it immediately goes into work, okay? So the change in temperature is 0. If the change in temperature is 0, okay, if the change in temperature is 0, which is written down here, okay, the change in my internal energy is 0, all right? And then that explains why work will be equal to the heat being put in, okay? So just again, the piston is free to move when heat is added, and it immediately transfers into work, okay, without changing the temperature of the gas. Okay, if my change in internal energy is 0, okay, then the change in temperature is 0. Remember that relationship? Therefore, this relationship becomes, if I put a 0 here, the change in work done by the piston is equal to the change in heat that I put in for an isothermal process. Those are pretty simple, okay? So the next video, we're going to talk about all the other types of thermal processes that happen in pistons.